We'll do a quick review of chapter 3 with f, f prime, and f double prime, because that'll help you with the packet. So when f is increasing, that means the slope is positive, right? Because if the curve is increasing, it's going up, the slope is positive, so f prime is positive. If f is concave up, you've got to understand what that looks like. Concave up is like bending up, so this is concave up. This is concave down. So if you see the curve kind of going like this, that means f double prime is positive. And if you see the curve bending down like this, that's concave down, so that would mean f double prime is negative. If f is flat, that means f prime equals 0, and that's what we call a critical number. So then the x value is called a critical value, a critical number. And that's where you might have a relative extremum. Also, if f has a vertical asymptote or a sharp turn, that means f prime is undefined, and that's also a critical number. So these are locations of possible relative extrema. So if we gave you the graph, hey, here's f, and that's what f looks like, and so there's A, B, C, D, name these things, B, C, D, E. Also, if f double prime equals 0 or undefined, that's where we have a location of possible inflection point. And an inflection point is where the concavity switches from positive to negative or vice versa. So when do you switch from being concave down to concave up? That's called an inflection point. So on this graph, what's special about A? A is a maximum. So f of A equals a max. What would we say is about f prime of A? 0. And at A is the curve concave up or concave down? Down, so we say f double prime of A is negative. B. What's f of B? That's an inflection point. So it's clearly not a maximum or a minimum, but if you look closely, this is where the curve is kind of bending down prior to x equals b, and then after x equals b, the curve is kind of bending up. I don't really know what else to say except that, like, the trajectory of its bendiness. So here the bendiness is down, there the bendiness is up. So that's an inflection point. And so let's talk about f prime of b first. F prime of b is, nope. Well, is this positive or negative? Negative, because it's going down. The curve has a negative derivative. But you're right, because we have an inflection point, so the second derivative, you can tell me the second derivative is 0. That means this thing is going to be where the curve has, the second derivative has a maximum or a minimum. So this is going from concave down to concave up. So the second derivative is going to go from probably a minimum. So it's decreasing to increasing. right? So f double prime is going to be negative and then positive. So that means f prime is decreasing and then increasing, so it has a minimum there when we have an inflection point. So that's what's a little tricky, the relationship between f prime and f double prime at inflection points. Where f prime has a max or a min is where f double prime can have an inflection point. Or f double prime can equal 0, and therefore we have an inflection point on the graph. I missed. All right, f of c. F of c is a special point because he's a minimum. And so f prime of c is 0. And concavity there is concave up, because its bendiness is up, so this is the second derivative is positive. I didn't map this out well, not a space. All right, d. F of d is special because he's a sharp turn. It's still a maximum. Because of the sharp turn, f prime is not 0, but it is undefined. If the first derivative is undefined, guess what the second derivative is? Also undefined. So once you have something that's undefined at a point, all further derivatives there will also be undefined. So if first derivative is undefined, then second derivative is also undefined, which means we got to think of this is an inflection point or not. Is this an inflection point? No, because we're concave up, and then we're still concave up. So even though that's where the second derivative is undefined, it is not an inflection point because the concavity doesn't switch. Yeah. Now I could adjust this so that it's a sharp turn, and so undefined, and is also a inflection point. That would be if I made it look like this.
No, I'm saying like literally at that point.
Oh, you want to say, is the concavity right here? Yeah. Right now? No. Because there's no bendiness at all. It's a sharp turn. So you don't have bendiness. You have a sharp turn. Then if there's a tiny little bit of bendiness, then there would be a first derivative as well, and it would be 0. And it would be concave down just for that tiny little interval. But you can't have concavity at a single point without also having concavity at an interval around that point. So if you're concave up all over here and concave up all over here, but you don't have, and you have a sharp turn, right at that point you don't have concavity at all. It's just second derivative undefined. So there would be a vertical asymptote on both of these things. So here you have a vertical asymptote where the derivative is going to infinity, and then negative infinity coming out from the other side. And then, because this is positive concavity on both sides, the second derivative is positive infinity on both sides of the vertical asymptote. If it were a sharp point, more like an absolute value graph, it would look like this. Instead of like bending into it, is this. But even this, I would say, I mean, derivative has a jump, but not a asymptote. Second derivative would be a flat line with a hole. And then E, yeah. E is going to be a lot like what other point we already have up here. So yeah, E and C are basically the same thing. Sam?
So the undefined does not exist.
Yes. Yeah. Undefined and does not exist are interchangeable here. So if the function, if the derivative is undefined at a point, then the derivative does not exist at all. Yeah. So yeah, when the packet says does not exist, it's the same thing as undefined. So that's the sort of kind of very brief review of chapter 3 here. Anything else we should talk about before we go back to limits? No, and Isan. Hopefully this is helpful for you guys so that when you go to the packet, you're not going yes. Since you weren't paying attention to writing it down. Yeah. A graph? Yeah.
You have F or F prime or whatever, and then some graph.
Here's F, like one of those things, but more intense.
Just graph the vector and
Yeah.
still graph. Because I'm going to analyze it. Oh, I see that.
What?
You didn't put that. No, I said I could do that when you didn't have the prime. And you go, oh, he wrote F and then wrote F again. And I was like, oh, I can rewrite F. Oh.
But this is what you had in mind. All right. So here's F, sketch F prime. Way out on the left, what's the slope of F? Positive or negative? Positive. It's going up. So F prime is going to be positive. F prime is going to be positive. And let's relocate this graph because so F prime is positive, and therefore, where is it relative to the x-axis? Above. And then where do we have our first special point? At the maximum. Let's give them a name, call this at A. So at A, we have a maximum. What's the slope here at A? 0. So we say F prime equals 0 right there at A. So 0. We start up above, and then we're going down to get to the x-intercept at A, where we have a maximum on F. Then, after A, what are we? Negative, because this is decreasing, so this is going to be a negative slope, so we're down here somewhere. So we're starting above, and then we're below, and then where's our next special point? At the inflection point, which is going to be a min on F prime. And then we keep going, and we have this minimum here. What's the slope here? 0. So we have 0 slope again at C, so that's like here. So we're coming down, slope is negative. We reach our minimum at the inflection point, and we come back up and hit the slope of 0 again at C. Then, sharp turn at D. As we approach that sharp turn, what's happening with our slope? It's increasing, and it increases infinitely. So we go into a vertical asymptote here and go whoop, whoop. So as you approach the vertical asymptote, as you approach the sharp turn, the graph of F prime turns into a vertical asymptote, and the slope is increasing into that vertical asymptote, so we go up the vertical asymptote. Coming out of the vertical asymptote, what's our slope? Negative, so coming out of the vertical asymptote, we're down here. And then, what happens right here at E? That's an inflection point. So that's an inflection point, and so that means our F prime is going to be 0. So it's a negative slope the whole time. So what the hell? Oh, okay. So that's E. That's an inflection point. So inflection point is when we have a minimum or a maximum on that prime. So we're always going down like that. We don't necessarily know exactly how high we get, but that's okay. It's going to be parabola-esque over there. So we have a negative, super very negative slope down on the side of the vertical asymptote. Then our slope is getting less and less and less negative until suddenly now our slope is getting more and more and more negative. So our derivative is coming up, and then it's going back down. The slope is always negative, so this is always below the x-axis. So then F double prime, it wouldn't be 2 lines because you have a vertical asymptote, but it would be 2 curves I do think it's worthwhile to think about this. So we have a D here, vertical asymptote. This guy's slope is negative, so F double prime is below the x-axis until we get to B, and then at x equals B, our second derivative is positive. So well, it can't be a line because you have the vertical asymptote blocking this off. So maybe it's one of these ones. So our slope is very negative. It's getting less negative. The slope is 0. Our slope is positive. Our slope becomes infinitely positive because we run into the vertical asymptote. Vertical asymptote blocks us off. It can't just be a line. Maybe it's more line-esque than that. But it's like that. It can't be a straight line because the vertical asymptote forces us to have a curve. And then over here, the slope is positive, then 0, then negative. So same sort of thing over 0. So that's what the second derivative kind of sort of looks like. So I don't think you need to sketch a second derivative, but on the packet, being able to read F and analyze it. I've made videos for the whole packet, but I've broken it down into like chunks. Maybe I'll publish videos for like one page of the multiple choice and one page of the response. And have you guys help there. All right. So I'll do that later today if I remember to. If I forget, somebody email me to remind me. Yes. Most of it was fine until suddenly it was very wrong. I think so. So I butchered this. So, the general theme of, hey, here's a limit. It's indeterminate form in one of these weird exponential ways. Create a new variable, y or v or whatever you like. Set that variable equal to the limit so that you can take the natural log on both sides and use that to escape the exponent out of exponent land. That's all good. Where I led us wrong was then when we took the derivative of both sides of the equation. I was confusing that with something called linear logarithmic differentiation, which we did like twice, way back in chapter 3, as a way to take the derivative of things like this. But that's not what we want to do here. So the first part of this was fine, where we say we're going to let y equal this limit. We called it v, okay? And that's when we got to v prime over v, that's where it's no. So cross that out. So then we take the natural log of v, and we took the natural log of the limit, and that was fine. Because whatever you do on one side of any equation, you can do to the other side. And we alternated, we swapped the order of the limit and the natural log, and that was fine. So we pulled the limit out of the whole thing and put the natural log inside the limit. And the reason for bringing the natural log into things at all was to allow us to get this exponent out of being an exponent. So you pull the x out of the natural log and have x times the natural log of sine of x. Meanwhile, natural log of v is just chilling. And then we do not take the derivative. Instead, we try to do the limit again and see what we get. So if we try to take the limit now, x is approaching 0, I think from the right side specifically. So this is going to be 0 times, what's sine of 0? 0 from the right. And the natural log of 0 from the right is undefined. You're going down a vertical asymptote. So the natural log of 0 is a vertical asymptote. If you're coming at that vertical asymptote from the right, you're going down the vertical asymptote. You cannot attack that vertical asymptote from the left because the natural log of negatives doesn't exist. The natural log of 0 is a vertical asymptote, so this is what ln of x looks like. So the limit as x approaches 0 from the right of natural log of 0 is minus infinity. And now here we have a different indeterminate form. This is better because here we can now turn multiplication into division. And that's what I should have done. So instead of doing the derivative, I should have said, let's turn this into division. Do you want to divide by the reciprocal of x, or do you want to divide by the reciprocal of the natural log of sine of x? Yeah, let's do x. That'll be a lot easier. So we'll have the natural log of e just chilling, and we have the limit as x approaches 0 from the right. And then instead of x times the natural log of something, we'll do the natural log of something divided by the reciprocal of x. That's 1 over x. And now, when we do the limit, instead of 0 times infinity, we have infinity divided by 1 over 0 is infinity. And what can we do now? Derivatize, specifically L'Hopital. Yeah, so now we can L'Hopital, because now we're in an indeterminate form that is L'Hopital. Nope. Because we're doing L'Hopital's rule, over here, so here's what this guy's job is to just be here so that we have an equation. But when we do L'Hopital's rule, does that change the value of the limit? Nope. It allows us to find the limit. So we're going to find the limit and then solve for v, because at the beginning we defined, let's let our limit equal v. So at the end we're going to e it. So we introduce a new variable, define this variable equals the limit that we really care about. Then we hide that limit inside a natural log. That allows us to then evaluate the limit. We do all the work we need to do to evaluate the limit. When we L'Hopital, we don't need to do anything over here to natural log of v, because when we L'Hopital, it's almost like we're just multiplying by fancy 1. It's like we're differentiating by fancy 1, sort of. You're not changing the value of the limit. You're manipulating this to allow you to find the value of the limit. And then once you've got the value of this limit involving the natural log, you e it to find the value of v, which is what we really wanted, because that's the value of the actual true limit that we're interested in. No. Plus infinity. Because 1 over 0 gives us a vertical asymptote. If we approach a vertical asymptote, the limit is some kind of infinity. Since we're approaching 0 from the right, 1 over a positive is positive. But as long as we have any kind of infinity over any other kind of infinity, that's L'Hopital. So then we do L'Hopital's rule. And what's the derivative of the natural log of sine of x? Cosine x over sine x, which we can turn into cotangent x. What's the derivative of 1 over x? Negative 1 over x squared. And instead of dividing by negative 1 over x squared, we could turn that into x squared over negative. So multiply by x squared over negative 1, or by negative x squared. And now, again, we're taking the limit as x approaches 0. We have negative x squared times cotangent of x. Now, why am I doing that? Because I don't want to deal with a fraction on top. I'd rather just deal with cotangent. And I don't want to divide by negative 1 over x squared if I can help it. I would rather just multiply if I can. So we're rewriting that as cotangent, rewriting division back as multiplication again. And now we hope and pray this works out. If we plug in 0 now, x squared goes to 0. And cotangent of x, what's cotangent to 0? That's undefined still. So cotangent has a vertical asymptote at 0. So this is 0 times some kind of infinity. Cool. So now instead of times it by tangent or cotangent, what could we do? Let's keep it in terms of like all one piece. What's the reciprocal of cotangent? 1 over tangent, right? So cotangent is 1 over tangent. So basically, these things switch so that x squared is on top and not a fraction, and then cotangent is down below as tangent. So this is negative x squared over tangent x. We have 0 over 0, right? So guess what we do again? More L'Hopital. This one's rough. This one's really, really brutal. So we L'Hopital again. Now we're almost there. We're almost there. Because now when we L'Hopital again, what's the derivative of the numerator? Negative 2x. What's the derivative of tangent? Secant squared x. Limit as x approaches 0. Negative 2 times 0 is 0. Secant, what's cosine of 0? So what's secant of 0? Also 1, because cosine, secant, reciprocals. So what's secant squared of 0? 1. So what's this limit? 0. Are we done?
Yes.
No, we're not done, because, remember, what is this?
Oh, it equals
ln of v.
Okay.
So we need to find out b, because b was the actual limit. So what do we do now? E. And we have b equals e to the 0 is 1. That's our actual limit. So that is...
All of that for 1.
Yeah, that's evil. So if you have one of these indeterminate forms that's an exponential, 0 to the 0 or infinity to the 0 or 1 to the infinity, they all kind of lead you in the same direction. Now, this one's especially nasty because you have to do L'Hopital's rule twice. You have to do L'Hopital's rule, see what you get, rearrange stuff before you L'Hopital again. It's up. But in all these cases, the trick is the same. Create a new variable, y or v or w, whatever you like. Define that variable as the value of the real limit. Then natural log both sides and go from there with the natural log, where this side just kind of sits here and waits until you finally have a limit, and then he's like, don't forget to eat. And that's the true limit. Let's do one more of these nasty things, and then we'll be done.
I got that one.
So,
That's it's the one before 63. Whatever the
62?
no, because it's every other odd.
Okay.
So
459?
Yeah. Wait, that one on Yeah.
No!
You know,
Is
I
it
wanna
this
say-
exact thing? I don't think it's this particular.
I want to say it's pretty similar, where you have to like ln pull the thing out and then ln at the end, the e at the end, because I forgot to e it at the end.
Okay. Last example. And then tomorrow what I want to do is go through Albert problems on L'Hopital's rule and see what you might see on like a multiple choice AP exam dealing with L'Hopital. All right. If you try to plug in infinity, what's 1 over infinity? 0. So the inside of this is just 1. And then it's raised to the infinity. And yeah, we don't know what that is. It might be 1, but it probably isn't. So we create a new variable. What do you want to call a new variable? P. P for, oh,
Pajama
poopy.
day.
We don't like this. Or pajama day. All right, so P equals this limit.
Why not just call it 1
Because we don't know what that is. But it's going to be something. Let's solve it. So let's find out what it is. So, well, we'll find out. Then what do you do? ln, the natural log of p, equals, and then let's save ourselves a half a step and just put the natural log directly inside the limit right away. Is that okay? Anybody object to that? Okay, thanks.
What was the purpose of the ln again?
To allow us to do this very next step, where we get exponent out. So we want to turn this into not an exponential thing. So now we'll have x times the natural log of 1 plus 1 over x. And now if you try to do the limit again, x is approaching infinity, and 1 plus 1 over x is 0, so this is infinity times the natural log of 1. And what's the natural log of 1? 0. So it's another indeterminate form. So in this case, instead of turning something into, well, yeah, it's a 0 times infinity sort of thing. So we turn multiplication into division. Who do you want to deal with the reciprocal of? X or the natural log of something? Yeah, good call. So you have limit, x approaches infinity. And now this is division. What's your numerator? Denominator is 1 over x. And now, if you did this, you would have 0 on top. And what's 1 divided by infinity on the bottom? 0. So 0 over 0 allows us to L'Hopital. Yep. A lot of math, actually. So when you L'Hopital, this particular thing, I'm going to come up with so natural log of p equals, what's the derivative of the inside here? Negative 1 over x squared. And then that multiplies to 1 over the inside. You have 1 over 1 plus 1 over x. Yeah, so derivative of a log is derivative of the inside over or times 1 over that thing. So this thing is over that. I forgot the limit. And then the denominator, what's the derivative of 1 over x squared? And then lo and behold, and we get natural log, so this works out much nicer. Natural log of p is the limit, you're right, as x approaches infinity, of just 1 over 1 plus 1 over x. And that's 1 over, yeah. So you get 1 plus 0. No, it's not 1.
No, it's ln.
All right, so E.
Because remember, this is natural log of p. And so now e, that's p equals e. So that's our limit, is e. And if you remember, this is how e is defined as a limit of that thing as x goes to infinity. That's where e comes from. Thanks, Mr. Euler, for giving us this thing. The guy who is named Leonard Euler. He gives his name to that number. What? The Euler constant. What is Euler? He's not Greek. Like Euclid.
You made the
How is that? Somebody did. So don't confuse Euler with Euclid. He was actually pronounced Euclid because he's Greek, and Euler is something Eastern European or Central European. Let's say German. So that's oi. That's you. Euclid. He's who you have to thank for all of geometry.
Oh, all of them.
Basically.
It improved.
Yeah.
That's
Yep.
cool.
Like all of his geometry.
Just kidding. I actually like
Wait, so
unpopular opinion.
Yeah.
I feel like down there.
Yeah. So yeah, Euler and Euclid, not Euler and Euclid. So tomorrow, if you have any more questions about Packet, bring them. That's fine. And then I want us to go through Albert L'Hopital stuff and see what does Albert have to say about L'Hopital and work through some of those together.
And what's the test?
And the test is Thursday, Friday,
Oh. You can do it like
Not Friday.
Thursday after
or take home.
Take home.
Take home.
Yeah,
Okay.
Is it just a L'Hopital rule? Will this be on the
And
test?
integrals. So 8.1, 8.7. So it'll be like, here's a number of integrals, integrate them. Here's several limits. Limit them.
Just like regular area interval. Is it not just integrals?
Just basic integrals. Like find the antiderivative.
Okay. Well, text it.
Anything we've done is fair game. Anything we've done is fair game. Including this.
Wait, what about the F? Will the F come?
That's not in chapter 8.
Okay.
So this is the
I
beginning
love
of
the test on
AP.
that.
This is AP exam review.
No, that would be the test. No, I want L'Hopital. No, I do not want that. That's
So I gotta decide if it's gonna be take home or Thursday, Friday.
20 minutes per body paragraph. Well, I'll be fine.
No, we don't want to come to school.
It's literally just a rough one. What's you do?
Can I tell you a secret?
It is.
What?
It's senior skip day on Friday.
No.
How's the Phillies home?
Yeah,
record,
exactly.
so.
We're fearing
So that
it
means-
anyway.
so
So
that
it
means-
won't be my problem. It'll be Gwen's problem. Yeah.